Okay, so here in section 8.4, we're looking at operations with radicals, and we'll start at the top here with what are referred to as like radical terms. And like radical terms are radicals that have the same index, and the same index just means that you're talking about both of them being the square root, both of them being the cube root, the little index number that's out here on outside of the radical. So it has the same value there, and it has the same value underneath the radicand. And so in this case here, both of these are 17, so they would be considered like terms. They're both the square root, and they both have the same value there. So if we were, for example, adding these two terms together, then we would add the whole numbers out here like we normally would. So -2 plus 8 would give me a +6. And then I just keep the radical part, so 6 on the square root of 17. It's kind of like treating it like a variable, like 2x plus 3x is 5x. You don't do anything to the x's, you just keep it. Same thing here. You don't do anything to the radical part, just keep it, and you're adding or subtracting the coefficients out front, or multiplying and dividing, as you'll see further. Right. In this set of notes, I'm not going to do every single problem because you still have that worked out solution key online in Blackboard. So I think what I'll do is about 3 questions per page, and then let you consult the solution key. We've shown our work on the solution key, so I think you'll be good. But if you need any help, always feel free to contact me. All right, so looking here at example 1, just like I didn't even realize this. Example 1 is exactly like what I just did here, the -2 square root of 17 plus 8 square root of 17. Like I was saying, you just take these two values here and add them together, which is, like we said, a +6, and they are both the square root of 17. Final answer. Okay. Example 2, the only thing different there is that they're all cube roots, so add up those numbers and keep that cube root. Okay, I'm going to move on down to example 3. You'll notice that all of these are the fourth root. Okay, so we will add up our numbers. So -3 plus 100, that would give me 97. And then you've got this minus sign sitting in front of this last fourth root. Remember, it's an imaginary -1. So 97 minus 1 would give me 96. So I have 96 on the fourth root of 9. Final answer. All right, and then we'll move on down to the very last one. You'll notice here, the first term you've got the cube root of 2x, and the last term you have the cube root of 2x. So these two terms are what we refer to as like terms, and I can combine those. This middle one has a different index. It's got the same piece underneath, but it's got a different index. It's the square root, so I'm not going to be able to combine it. I'll just have to add it as part of my answer. So 6 plus 6 will give me 12 on the cube root of 2x. And then I just bring down this middle term here, so -6 on the square root of 2x. That's our final answer. Like I said, in order to be able to combine them, you have to have the same index up here, which we don't, and the same value underneath here. So since we don't have that same index, then I can't include that one. Let me erase that little bit there that I was just writing so it doesn't look this way, like a minus sign or anything. All right, we'll flip it on over then to the next page. On this page, we are looking at still looking at adding and subtracting radicals, but sometimes you'll see that they're not exactly the same. You won't be able to add or subtract them if they don't have the same piece underneath the radical, but sometimes they can be simplified, and then the terms underneath the radical are the same. So like, for example, in example 1, you have 3 square root of 8 minus 5 square root of 2. Well, they're both square roots, but these are not the same values underneath here, so I can't just go straight away to trying to combine these. But remember our list of square roots, perfect squares, right? So 2 squared is 4, 3 squared is 9, 4 squared is 16, 25, 36, and so on. So we think of the highest number in this square root list that will divide evenly into 8, and hopefully you agree that, oh, well, that would be 4 times 2. And then you have minus 5 square root of 2. I can't break up 2 any further. There's not a number here in my list that will go into 2 evenly. But now if I clean this up, the square root of 4 is 2. 2 times the 3 that's already out here is 6. So I have 6 square root of 2 minus 5 square root of 2. Now it's legal for me to combine these. because they both are square roots and they both have 2's underneath. So I just combine my numbers. 6 minus 5 will give me 1 square root of 2. And you could just simply write that as the square root of 2. Either way is fine. Okay. All right, if we move on down then to example 3. In example 3, you have 8 square root of 27 plus 3 square root of 75. So at the moment, if you weren't thinking about reducing, you couldn't go any further, but these can be reduced. We think the highest square root that'll go into 27, we agree with that, would be 9 times 3. The highest square root that can go into 75, 25 times 3. Right? 9 times 3 is 27, 25 times 3 is 75, so they're still the same values. Now let's take the square root of the pieces that we can. The square root of 9 is 3. 3 times this 8 is 24. And then we leave that square root of 3 inside the house. Square root of 25 is 5. 5 times 3 is 15. And then we leave that square root of 3 inside the house. And then 25 plus 15, that 39, and the square root of 3, final answer. And then we'll look at example 4. It's cube root this time. So cube root, we need to think about our cube root list. So remember, oops, sorry about that. Our cube root list is cube root, so 2 cubed is 8, 3 cubed 27, 4 cubed 64, 5 cubed 125. That's as far as I need to go. All right, so I look for the highest number in this list that will divide evenly into 40. And so hopefully that one's pretty obvious to you. Oh, 8 will go into 40. 8 times 5 minus 135. And this one may not be as obvious to you. It wouldn't be to me. You just start going through your list. 135 divided by 8. That won't go evenly. 135 divided by 27 though. 27 times 5. Okay. Now we take the cube root. So the cube root of 8 is 2. So it comes outside the house, and then that 5 stays inside. Cube root of 27 is 3. So it comes outside the house, and the 5 stays inside. So now I'm able to go further because these are both cube root of 5's, same index and same piece underneath the radical there. 2 minus 3 is -1 on the cube root of 5. It's like the last or the previous one that I had done before for you. You can keep that 1 there, or you can just write it like this, negative cube root of 5. Same thing. Either way is fine. Okay. All right, we'll flip it on over. Got an extra page there. Let me just delete that page. There we go. All right. Okay. All right. So on this particular page, we are looking at multiplying radical expressions. So you'll be looking at the distributive property as well as FOILing. Okay. So I'm going to do a couple on this page. So in the first one, hopefully you recognize, hey, this looks like distributing, right? You've got one term on the outside of a parenthesis, so just take that square root of 2 and distribute it through. The square root of 2 times the square root of 10 will give us the square root of 20, minus square root of 2 times square root of 6 will give us the square root of 12. So again, think about your square root list. 4, 9, 16, 25, 36, and just put a dot, dot, dot. It just keeps going. 7 squared, 8 squared, and so on. We look for the highest number in that list that will divide evenly into 20. Hopefully you agree with 4 times 3. Highest number evenly that will divide into 12. It's also 4. 4 times 3. So then that gives me, you know what, hopefully you just caught me there. 4 times 3 is not 20. 4 times 5 is 20. There we go. Good. So now from here, take the square root of the pieces that we can. Square root of 4 is 2. So you've got 2 square root of 5 minus, on the next piece, square root of 4 is 2, square root of 3. That's fully simplified, but I'm not going to be able to subtract any further because the pieces underneath the square root, underneath those radicals there, are not the same. So that would be your final answer. 2 square root of 5 minus 2 square root of 3. All right, I'm going to move on down. I'm going to do example 3 with you, just because there's a little bit more to be done on that one. But example 2 is the exact same way. Okay, going to actually, you've got a 2 term times another 2 term, so you're going to want to FOIL on this one. So multiply my first. Square root of 3 times 5 square root of 3 would be 5 square root of 9. So there's your first. Outside, square root of 3 times 2, so plus 2 square root of 3. Inside, 1 times 5 square root of 3, 5 square root of 3. And then last, 1 times 2. All right, so now we should start cleaning up. We know the square root of 9, right? That's just 3. These two middle terms here are like terms, so we can combine those, and that would become 7 square root of 3 plus 2. Now, up here at the front, 5 times 3 gives me 15 plus 7 square root of 3 plus 2. And then I've got one more set of like terms. 15 plus 2 would give me 17 plus 7 square root of 3. Final answer. I showed a lot of steps there. If any point, like for example, right here when you did the 5 times the square root of 9, when you did the square root of 9 is 3 and 3 times 5 is 15, you could go straight from there to there if you like. I just showed a lot of work. Okay. Example 4 is another foiling, so I'll let you try that one. Example 5, this one sometimes I see folks, it's not it's really not too different than anything we've done so far, but folks often forget to write it twice and FOIL it. Anytime you have a 2 term here, you've got a square root of 5 and a 1 separated by an addition sign, or if it was separated by a subtraction sign, whatever the number is up here, that tells you that you need to write that value inside that parentheses. So square root of 5 plus 1 times itself that many times, so I need 2 of these. If it was to the 3rd power, I'd write it 3 times. And now you FOIL, okay? Common wrong answer I see folks do is just square the 5 and square the 1, okay? But you actually got to FOIL it. So square root of 5 times the square root of 5 will give me square root of 25. Outside, square root of 5 times 1. Inside, 1 times the square root of 5. And then last, 1 times 1. Square root of 25 is 5. These two square root of 5s here combine. There's a 1 and a 1 in front of both of those, so you get 2 square root of 5s plus 1. And then combine your whole numbers here. 5 plus 1 will give me 6 plus 2 square root of 5. Final answer. Okay. And then let's flip it over to your last page. And on this page, we'll talk about rationalizing the denominator. So in rationalizing, generally when you move forward into pre-calculus, you'll find that a lot of times it's not legal to leave square roots in the denominator, and so we use a technique that's referred to as rationalizing the denominator in order to get rid of the square root, or it could be any kind of root in the denominator. So here our directions say to rationalize the denominator, divide and simplify. Okay, so like we talked about in the last section, one big square root is the same as 2 small ones. So the big square root here of 7/3 is the same as the square root of 7 divided by the square root of 3. Now I don't want to leave that square root in the denominator, so the rule is you just multiply by whatever the square root is in the denominator. If you do it to the bottom, you got to do it to the top. So if that had been the square root of, I don't know, 7 in the denominator, I'd multiply top and bottom by the square root of 7. If it had been the square root of 11 in the denominator, I would multiply the top and bottom by the square root of 11. Now you just multiply straight across. So up top, the square root of 7 times the square root of 3 is the square root of 21. And then on the bottom, the square root of 3 times the square root of 3 is the square root of 9. And we can clean that up. The square root of 9 is just 3. In general, anytime you take a square root and multiply it times itself, you always get what is underneath the square root itself. So you technically could bypass this step here that I was showing. The square root of 3 times the square root of 3 is just going to be 3. Okay. It would never change. It's kind of like on the previous page where we had down here at the bottom, these past 2 problems, but the square root of 5 times the square root of 5, I could have just gone straight to, it was 5. Okay, but I was just showing my work there on this one. the square root of 3 times the square root of 3 would have just been 3 but instead I put the square root of 9 there. I mean, it is that, and square root of 9 is 3. I'm just trying to show you that there's, like, I guess, a little bit of a shortcut to that, okay? I'll let you try example 2. We'll move on down to example 3. So here in example 3, I've got a square root in the denominator. Sorry about that. I've got a square root in the denominator. I can't leave that there, so I multiply top and bottom by that square root. So I multiply by the square root of y. So then up top I have the square root of 8x to the 5th y squared. Over on the bottom I have 2, and if we use our property that I was just telling you about, the square root, or our trick, or our shortcut, the square root of y times the square root of y is just y. Okay. Alright, so now up top I just need to clean up. I need everything to be number wise. I need to be able to take the square root of the value, and then exponent wise I need these to be multiples of 2. So I can rewrite 8 as a perfect square, so 4 times 2. X to the 5th I can rewrite as x to the 4th times x, and then I've got my y squared. All that's underneath the square root, and then on the bottom I still have my 2y, and it's outside the house. I've gotten rid of that square root. Now I just come through and I take the square root of all the terms that I can. So the square root of 4 is 2, so that's outside. The square root of x to the 4th, x squared. Square root of y squared, y. And so then left inside I have a 2x, and then on the bottom I have here 2y. It is legal at this point to cancel out anything on the top and bottom that are alike, or reduce, if you think of it that way. So let me get a different color here. It is legal that these 2's would cancel out, as well as these y's. So then that would leave me as a final answer then as x squared on the square root of 2x. Okay. I think I'm going to finish up this page with you because there's a little bit different things going on in both of these problems. So far everything that we've done for rationalizing the denominator have all been square roots, but the next one is a cube root. The same rule applies. You just multiply the top and the bottom by that same value. So I'm going to multiply top and bottom by the cube root of 3c. Cube root of 3c. So that same trick works, that if you take anything and multiply it times itself, so it's cube root times cube root, I'm just going to get 3c down here below, okay? And then up top I have the cube root of 3 times 2 will give me 6ac. And then I'm not going to be able to take the cube root of 6, and nor I can't write a and c as multiples of 3, so that would be your final answer. All right, in example 5, this will be a scenario that you see quite a bit in pre-calculus. The technique here is a little different. This is, you'll hear it phrased as multiplying by your conjugate whenever you get to pre-calculus, but you're multiplying here by 2 plus the square root of 7. I can't just simply, because of that minus sign down there, I can't just simply multiply top and bottom by the square root of 7. So I have to multiply top and bottom by 2 plus the square root of 7. This is just sort of giving you a little bit of a foreshadowing going into pre-calculus. So up top you've got 3 times this 2 plus square root of 7. So hopefully you can see here, oh, I need to just distribute that 3. So that would give me 6 plus 3 square root of 7. And then on the bottom you've got a 2 term times another 2 term, so you're foiling. So your first 2 times 2 gives you 4. Outside 2 times square root of 7, so plus 2 square root of 7. Inside 2 times negative square root of 7, so minus 2 square root of 7. And then your last square root of 7 times the square root of 7 is just 7, and it was a negative times a positive, so I put the negative there. Let's start cleaning up a little bit. So the top I can't do anything with yet, so 6 plus 3 square root of 7. On the bottom, these 2 square root of 7s, one's positive, one's negative, so they cancel out. 4 minus 7 gives me negative 3. Now, I mean, I guess technically you could leave it like that, but I guess fundamentally in math, they typically don't leave the negative in the bottom. And then also, use a different color here, all of these numbers outside the house have something in common. 3, 6, and 3. Since they all have something in common, I can go through and divide everything by 3. And what I would do in this particular case is I'd go through and divide everything by -3. So I would, give me just a second. There we go. So let me get a different color as well. Here we go. I'll divide by -3. So it would be here, it would be 6 divided by -3, 3 divided by -3, -3 divided by -3. So on the bottom, you're just canceling out and you just have 1. We'll leave that there just kind of so you can see it. 6 divided by -3 will give us -2. 3 divided by -3 will give you a -1 on the square root of 7. So we could just clean that up and just say, okay, well, this is -2 minus the square root of 7 as our final answer. Okay. So again, that last one is referred to as multiplying by what's referred to as a conjugate. And the conjugate keeps the same first and last terms. It only changes the middle sign whenever you do that. And essentially, and you saw here, it gets rid of the square root in the denominator. That's the deal with dividing radicals. You want to get rid of the square root in the denominator. All right, let me know if you need anything. Thanks a lot. Bye.